All right, hey, good morning. Let's get started. We're going to go to chapter 5, and especially for you guys online, but also for you guys in person. You might have noticed I gave an extra window, an extra day for the test. So you have the ability to take the test online either Wednesday or Thursday, and I'll say it again. We said it right before we started the video, but for you guys who are in person, if you want an extra day and you want to take it on Thursday, you're welcome to do that. Of course, you're going to have to do it then through Canvas and online. So that's options out there. So our plan here for today is to start chapter 5. You'll see it's a continuation of Newton's laws. I mentioned that already, that Newton's laws, we see it for the first time yesterday in chapter 4. We'll just keep going with that in chapter 5, and we'll keep going with that in chapter 6. And of course, you probably remember that the original plan for test 1 was chapters 1 through 6, so it included the 3 chapters on Newton's laws, but I decided that would be just too much rushing. So hopefully we'll get into chapter 6. I think it'll even help you get ready for the test today, but the stuff in chapter 6 will not be on this exam. They'll be on the second exam. Okay, so like I said, we'll blast through 5 real quick and do a bunch of examples. That's what we'll spend most of our times. Question? Yeah.
Actually,
Never mind? Okay. All right. So, and unless I'm missing anything here, let me continue on. As I mentioned, Newton's 3 laws of motion are, in one sense, very simple because they're just 3 sentences. And if you can remember those 3 sentences, and the big one is Newton's second law, where you take the net force, which means you add up all the forces, which means you have vectors. So that's a lot of work in itself. But if you add up all the forces, you set that equal to ma. And the best way to do that is those 4 steps. You first get a good physical picture of what's going on. That way you can draw a free body diagram. That way it'll make it setting up the equations a lot easier, and then finally solving the equations. And so those are kind of my 4 steps, my 4 suggestions of how you think about all these problems. And we started with ones that are as easy as we can make them in chapter 4. And now let's go a step further. And so what are we about to do? Well, part of me just wants to say the same thing. So that's going to make it a short and easy chapter. However, it's the same thing, but we're going to take a deeper dive into friction. And so we're still going to be talking about forces. We're still going to be talking about Newton's laws, but now we'll talk about friction a little deeper. So that's where this chapter 5 begins, and that's why I think a good title for chapter 5 is More About Forces. And the 2 we want to look at in more detail, the first one being friction, and the second one being that air resistance or the drag force. And so I'll start here with I'll call it a deeper dive into friction. But before, let me just backtrack to last lecture, chapter 4. And so if we had something like a block sitting on a table, oh, what a surprise. I have a block sitting on a table right here. Let me unhook the scale. And so here's the block. Now my block's not very heavy, so I'm going to just put a little more weight on it so it's heavier. So kind of ignore this. Just think of this as the part of the block, okay? So my system is the 2 together. Okay, and so don't worry about the forces between them, just one big block. All right, so this is my way of making a heavier block. All right, so I've got this block, and if I were to ask you then, what are the forces on it? Well, this is our first step towards that free body diagram. And so if I come over here, and maybe in my physical picture, maybe even draw the table and say, all right, the forces would be everything in contact with it plus gravity. That was kind of my description last time in chapter 4 as we were getting started. We talked about pushing somebody or pulling somebody. We could have a rope tied to them. But all these forces I talked about had something contacting it plus gravity, the weight of it. So if I were to say, all right, what is the free body diagram here? I guess maybe I would start with the weight of it, which we learned was mg. And then, of course, it's in contact with the table. And so that was what I classified as a normal force or a little compressional force. And at the moment, I would say that's all there is. But if I take one more step and go, okay, what if I connect something to it and pull? And so this is a little scale so we can kind of get some numbers on, okay, how much am I pulling? And so let me just pull with 2. And the units are newtons. So I'm pulling with 2 newtons, or maybe I can pull harder, 3 newtons, or even harder, 4 newtons. Maybe I'll just keep it simple at 2. Okay, so I'm pulling with 2 newtons. But as I'm pulling this, and I come over here to this free body diagram, I would say that then there is a force F. And I'll kind of leave it as equal to, and I'm just going to leave that blank for a second. But you can see when I was over there, I was pulling it with a force of 2, and yet it didn't move. Ooh, what does that tell you?
There's friction.
Yeah, see, there has to be a net force of 0. Remember Newton's first law from the last chapter, right? If the net force is not 0, there will be an acceleration. And of course, if the net force is 0, there'll be no acceleration. So as I was pulling that with a small amount of force, too, it didn't move. So that would tell me that the net force has to be 0, which would then tell me that the interaction between the two surfaces is producing a friction. And that's nothing new. That much we all talked about in the last chapter. But I just want you, as I say, I want to take a kind of a deeper dive here, and your author gives you a couple of really good pictures here. Let me start with the first one. He says, you know, why is there a little bit of friction? And I think I kind of touched on this a little bit. And this picture, I think, shows it pretty well. There's their box on some kind of surface, and it looks like, you know, the attempted pull is kind of the opposite of mine, but they're saying some friction, and then they look at the surface between them, and it's kind of rough. And so they're going to bump and rub each other, and that's where that friction comes from. Now, if we look a little more closer at this friction, watch something interesting. All right. So if I pull with 2, how much should the friction be? 2. Again, how do I know that?
Because it's not moving. So
Yeah.
the friction needs to be more than 2 or 2 that it stays.
Okay, so Newton's first law would say the net force has to be 0. And if I come over here and just look at the horizontal forces of this free body diagram, if I'm pulling this way at 2, then this must be pulling back with 2. Exactly. Not more than 2, not less than 2, but exactly 2. Because if these two did not balance, then you would have a net force. Then you would have an acceleration. And clearly that is not accelerating. It's just sitting there. All right. Now, watch this. I'm going to pull a little harder. So let's see, I was pulling with 2. So let me give me something to push off of. So now let me pull 3. What's the friction now?
3.
3. I'm pulling with 4. What's the friction?
4.
Now I'm pulling with 5. What's the friction? 5. Now I'm pulling with 6. What's the friction? Okay, so do you see how the friction is a bit complicated? It is not a set number. You see that? The friction here is whatever the number needed to be in order to push back, in order to keep the net force from 0. And again, you can kind of see this, I think, in how these things are kind of locking together. I'll kind of use my fingers, but if I have kind of some rough edges on the table and some rough edges on the block, and they kind of go in between, and I pull the block this way, they're going to bump into what I'll call the hills and the valleys. They'll kind of lock together. But if I pull it even harder, that just makes them push into the hills and valleys even harder, so they push back even more. And so that's why the friction can be kind of complicated. That's why we're taking a deeper dive here into friction, because unfortunately, I can't just say the friction is a number and go, okay, it depends. And so it gets a little more complicated. So I'm going to do this. I'm going to say then the friction, and instead of saying equals, I'm going to say the friction is some parameter. It could be as low as 0, but I do want to then emphasize there is a maximum. And so notice I put an inequality there. No, let's watch it again. And so if I pull with, say, 3, friction is 3. If I pull with 4, the friction is 4. If I pull with 5, the friction is 5. If I pull with 6, if I pull with 7, if I pull with 8, if I pull with 9, if I pull with 10, oh, now it's starting to move. So do you see how the friction could be some inequality? It goes up to some maximum value. And now it begins to move. Did the friction go away once it started moving? Did you see something interesting here? Did you see that before it started moving, it went up to some maximum? Then when it started moving, it went to a lower value? Oh, let's watch it again. So if I pull, there's 5, there's 6, there's 7, there's 8, there's 9, there's 10, or almost 10. And now, whoops, no, I got stuck on something. But maybe I'll show it again then. So here's 10, here's 11, 10. I'm really stuck on something. So, oh, there it goes. So now it breaks free. And what I'm trying to show you here is that if I plot the friction based upon a comparison of how much my hand is pulling, as long as it is not moving, those are equal. But at some point, I get to a maximum, and then it looks like it drops down, and this part is kind of hard to indicate, but it'll stay the same no matter how hard I pull it. And so if I got it moving and was pulling it really fast, and so if I pull it really fast, it stays about the same, or if I pull it slow. And so it's because of this we divide the friction into two categories. We say that if there's no sliding going on, we'll call it static friction. Then there is some maximum value. So let me indicate by putting a sub S next to the friction. And so the static friction then is an inequality. It is a amount. Oh, did we ever do a sound check? Oh, we did. Yeah. Okay. It's an inequality, and then says up to some maximum. But then once it breaks free, we refer to this then as the kinetic region. There is sliding going on. So let's call this the kinetic friction. And here's the interesting part of kinetic friction. It's just an equality. And that you're going to appreciate. And that means if it was sliding at a slow speed or a fast speed or a medium speed, it's just equal to some value. And that is much more useful. That I can say, hey, the friction is 7. It's going fast. So what? It's 7. It's going slow. So what? It's 7. As long as it's sliding, I have a constant value. So we're going to have to always start our problems and look at, is there any sliding going on or not? Some of these are easy, some of them aren't so easy. For example, right now, if I were to pull on this, I'd ask, okay, A, do I have any friction? And B, is it static friction or is it kinetic friction? Well, yeah, I have friction because I'm pulling on it, but it's not accelerating, so there must be a pushback, so yes, there must be friction. And since there's no sliding between the block and the table, it must be static friction. And of course, if I was sliding along, I would say, yes, there's friction, and yes, it must be kinetic. That one I think is easy to see. But what about if I'm walking along on the stage here, and I'm asking about the friction between my shoes and the stage? Well, first of all, I guess I would ask, is there any friction? And say, well, certainly there's got to be, right? This was our discussion before, that how do I get myself to go that way? I take advantage of Newton's third law. I push on the stage, so the stage will push back on me in that direction, equal and opposite. And so it's the stage that's pushing me forward. And if I had this rug that wasn't tied down, I might crumple it up instead of actually pushing me forward. Okay. But is it kinetic friction or is it static friction? Oh, good. And I hear both. And again, notice I said the friction depends if there's sliding between them, not if it's moving. And I think that one is what makes it hard, because even though I'm moving, it is not kinetic friction. There is no sliding between my shoes and the floor.
So it would be your ankles and your knees that would have kinetic friction.
If you're talking about the joints moving in there? Yeah, so they would be rolling against each other and have a kinetic friction in there. Sure, yeah. A car. And I should say a car under normal conditions, as it drives down the road, would that be static friction or kinetic friction? Static, because under normal conditions, you do not have any sliding between the tires and the road, right? The tires are turning, they're making contact with the road, they don't slide. Now, in the unfortunate circumstance that, say, a dog runs in front of the car and somebody slams on the brakes and the wheels lock up and now they slide, you would say, hey, the car's skidding. Would that be static or kinetic? So now that would be kinetic, because now there is some sliding between the tires and the road. So like I said, sometimes it can be a little bit hard. By the way, why do most cars anyways, I think almost all cars these days, have anti-lock brakes on them?
To prevent skidding.
Okay, to prevent skidding. Why? let's say it's not even raining. Let's just say the dog runs in front of me and I slam on the brakes.
Is it to give it give so there can be more more kinetic friction as opposed to static friction?
Yeah, did you see that the maximum amount of static friction is actually greater than the kinetic friction? And so you might at first think that, oh, if I just lock up the wheels, if I just go to a slide, that's going to stop me the fastest. No, that's not where your most friction is. Your most friction is at the point where you are on the brake enough to get to the point where it's just about to slide, but not completely sliding. And so that's why the computer's there, because if the dog runs in front of you and you slam on the brakes, first the hydraulics push in and they lock up the brakes, and the computer then takes over and says, whoa, clearly you want to stop this car fast. But if you start skidding, that is not better than if we ease up on the hydraulic pressure a little bit and let the wheels keep rolling, and they're right at the point of beginning to slide. That's going to give you the most friction, and that's going to stop the car the quickest. And so that's where the computer kicks in and says, okay, I'm going to take over here. You're pushing the brakes too hard and you're going to skid. Of course, you also lose control of the car too. So both of those are a big advantage of having the anti-lock brakes. So again, I just want to emphasize here, as we do our friction, we're going to divide it into two categories, a static and a kinetic. And we've got to kind of recognize, is this a static friction problem or is this a kinetic friction problem? All right, well, let's keep talking here, because as I think the author does a pretty good job in figure 5, he says, okay, taking a deeper dive into this, he says, what might affect the amount of friction? And you might see it here again. Remember, my largest static friction was at about a 10. What happens if I was pushing down on this?
And it's a larger limit.
Yeah, and I'm hoping kind of in your gut you can feel, as this picture's trying to show, that if there's only a little bit of force between the two surfaces, so if the normal force is kind of small, there's kind of a little gap between them. But if there's a large normal force and squeezing them together, it's going to be harder for them to rub apart. For mine, you might see it if I pile up some more weights here. And that's going to make a stronger push down between my surface. And so now if I pull on it, 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 pull on it. Uh-oh, I didn't want to go over the scale. Okay, a little too much. All right, so if I pull on it and pull on it, oops, and so what am I, about 16 right there? And then it starts to move. But what I'm trying to illustrate then, in both of these cases, this is, and I'm going to use a little math symbol, proportional to the normal force. And so how much is between them? Now, I think you could also agree that it would be determined also by what is the material that is between them. You know, is this wood sliding on wood? Is it something smooth, like a polished stainless steel on top of a polished aluminum? And so those are the two factors, and we give a little number to this. We use the Greek letter mu, And it is those two factors that is part of our deeper dive here. What are the two frictional forces, and what are the two factors that determined how much friction there is? And so let me put those four things together. The first is the static friction, and the second is the kinetic friction. The static friction, as I said, is a little bit harder, I think, because it's an inequality. It can go up to some maximum value. But both of them depend upon the material, and so we like to say it has a coefficient of friction, a coefficient of kinetic friction, and then the normal force. And the same thing here for static friction. The two factors that go into play are what is the material and what is the normal force. Now, the normal force is part of what we're studying, so a lot of times the normal force is the weight of the object, but I want to emphasize not all the time is the normal force the weight of the object. For example, maybe to keep it simple, I'll actually then just remove those. Right here, since it doesn't go up or down, I know that the normal force is equal to the weight because it's being pulled down by the weight of it until then the table has to lift up, and since the acceleration is 0 in the vertical direction, it must equal the weight. So the normal force is the weight. This is a good example of that. But if I was pushing down a little bit, then I would say there's two forces down. There's the force from my finger and the force of gravity. That has to be matched with the normal force. So in this case, the normal force would be more than its weight. It would be equal to the weight and the force of my finger. And so I just want to emphasize it's the amount of force between the two. It's not the weight of the object. Now, I've got to admit, many times the normal force is just simply the weight of the object. Instead of pushing down, I could kind of lift up. In fact, if I were to do this, see how it moves at a much lower force now? What? Oh, even with the one weight on here, sorry. But if I were lifting up at an angle, well, see if I can get a better one. Well, that's not quite what I wanted to show. But what I wanted to indicate here is I could have another force that is slightly up, and that way, again, the normal force does not necessarily equal the weight. What has to come out to be 0 is all the upward and downward forces. And so if I have a force that has a component that is upward, it doesn't equal it. Well, I'm getting way ahead of myself because I want to show you that in some problems here. But I just wanted to say then, the normal force, we're going to have to think about the problem that we have at hand. Many times it is the weight, but it is not always. So we got to look at that. Now, the material itself, for that one, we're just going to trust the engineers who measured a bunch of samples for us and go to this table. And so if we need to find the friction, remember this table. I believe it's number 1. Table, yeah, 5.1. And so if you ever have a situation that you have a rubber on dry concrete, it sounds like a good problem. Doesn't sound like a car tire on a concrete road. Then I can find the coefficients right here from this table. And did you notice that the coefficient for the kinetic is smaller than the static? Matching what we said earlier, that the maximum static is going to be greater than the kinetic. And you can see that in the equation. Same normal force, but the one that has the bigger coefficient is going to give us the bigger friction, or at least the maximum for this one, because this is an inequality. And so this right here, this product together is the largest it can ever be. And that's why if you scan that whole chart, you will see in every case the static friction one coefficient is a little bit higher than the kinetic one. And so you're always going to have this scenario where the maximum static friction is always a little bit more than the kinetic one. And of course, it depends what things are rubbing. I mean, here's a good one. How about steel on steel with it being oiled? You would expect that would probably slide really well, have very little friction. And sure enough, look how small those coefficients are. Or Teflon on steel. Here's the one you were talking about, the joints, and again, really low.
Is there a reason why the Teflon is equal?
Oh, it is equal, huh? I suspect there is a small difference that shows up in the next decimal places. But it's bottom line is it's very little friction, yeah. Yeah. Anyways, maybe I better not spend too much time here, but I just want to say if you're reading the problem and they start talking about somebody on a pair of skis going down the mountains on a spring day, you're like, okay, skis, those are probably waxed. They're probably on snow or ice. It's spring, so it's probably in the process of melting. So, okay, so I would probably jump up here and go, waxed wood on wet snow. Okay, all right, what is it? Now, do they have dry snow here? Wood on wood, wood on wet snow. Oh, okay, so they didn't include it in this table, but.
Dry snow would be ice on ice, right?
Wood on ice?
Ice on ice would be dry snow?
No, I don't. I think we want the wood on the ice, not ice on ice. And better still, probably a waxed wood. Anyways, I don't think we'll give you any problems that don't get covered in that chart. That's the bottom line here. All right, but this is our deeper dive into static friction. And so soon, what I want to do is just call up a bunch of more examples from the end of your book and say, all right, let's do the same type of thing that we were first exposed to in the last chapter, and let's just keep doing the same thinking, but now let's do it where we can focus a little bit deeper on the friction. Now, before we do that, though, let's also talk about the second force we want to dive a little bit deeper into, and that's the air resistance or the drag force. So let's talk about drag forces. And drag force is a lot like the frictional force. Sometimes we even get lazy and call it friction, but we really like to use that word friction with solids on solids, whereas a solid going through a fluid, and so maybe a submarine through the water, or an airplane through the air, or a car through the atmosphere. This object then, and I'll just kind of do it with a ball dropped from a high height. As the ball falls, it's going to bump into molecules that make up the fluid, and so it has to push them out of the way. So using Newton's third law, I would say here the ball pushes on the molecules. So what do the molecules do? Push on the ball. And that then is going to be our drag force. And so if I were to do a free body diagram here, So free body diagram, and I just drop a ball, I would say the forces are gravity and everything touching it. And in this case, the only thing touching it are the air molecules. That is the drag force. So I'll put, here's gravity, mg, and here is the drag force. And of course, up to this point, we've kind of ignored the air resistance, and we just said that the force would be its weight, mg. But now when I put here the drag force on here, it brings up the question like we just had. What factors come into play with the drag force? If you imagine this ball moving through the air or an airplane moving through the air, what do you think would affect its motion? Okay, how many there are? So I would agree that probably one of these factors, I'll put it right here, would be the density of the fluid. Probably means it would get harder to move through water than through air because there's a lot more molecules to push out of the way. Anything else you think might go into that? Temperature I'll bury in with the density. That kind of changes with the density. So I think, I don't disagree, but I think it's buried in with that statement. Anything else? Okay, I heard wind, but I think maybe a better way of saying that is the relative speed between the object and the fluid. Right? It's not so much how much the wind is blowing, but it's how fast is the object moving. And that's the big one I really want to focus on. Do you see how if this ball was going slow, in 1 second it would only hit maybe these molecules. But if it's going fast, it's going to hit a lot more molecules. In fact, it probably hits twice as many molecules. And if it did that, I would say its velocity raised to a power of 1. But if it's going really fast, something interesting can happen. Not only does it hit those molecules, but it hits them so hard that they have to move with the object. And so I would say it depends on the velocity twice, right? Because isn't the number of molecules you hit depends on how fast you're going, and the number that you drag along is also depending on how fast you're going. So I put a little or here because here's what we're going to do. We're going to say for things that are going slow, we'll just say that they kind of move through here. You hit the molecules and you just kind of move them out of the way, and then they kind of flow around the object and move back. And so if you double your speed, you double the number of molecules. So we would call that a proportional pattern. But watch this. If you drag them with you, so you're going really fast, when you double your speed, not only do you hit 2 times more, you drag along 2 times more. And so you have to have velocity times velocity. And so this is going to be velocity squared. Now, you don't have to make a decision whether it's going to be a fast or a slow. I'll help you out with that. Because this, like I said, is a deeper dive, but it's not what I would call an extreme deep dive. It's just something to help you guys understand why sometimes we're going to use a drag formula that only has velocity, and sometimes we will do velocity squared. I would also say then it needs to be, I guess when it's going fast and low density is when you kind of drag them along. And that usually happens in the air. So if we're talking about a car or an airplane, we usually use velocity squared for something like that. But something that here is going slow, and because it is also in a high density, what ends up happening is the molecules just flow around the object. So the number you hit is just directly proportional to how many you have and how easily you can flow through. So we'll talk about viscosity in that case. But there is this density. I think I heard somebody else say it. Wouldn't it, again, depend on how many molecules you hit? So wouldn't it depend not so much on the volume of it, but what you might call its cross-sectional area? How many it actually hits? Like if you had a long arrow, the molecules it actually hit is like cutting the arrow in half and saying, okay, it's that little circle right there. And so this right here then is what we refer to as the cross-sectional area. Somebody else said, what shape does it have? And those will be the four that we're going to focus on. So how difficult it is for something to get through depends on these factors. And the shape is a factor that, again, the engineers would just go, say, into a wind tunnel, change the shape and see what happens. And so if it's a sphere, if it's a bullet shape, if it's a cigar shape, if it's a triangular shape, whatever the shape is, then we can give a number associated with it. And that's why your author, like table 1, has table 2 here. Table 2 is kind of this deeper dive here and says, okay, what is the shape of it? And so to make our problems kind of a little more interesting, they give us the shapes of different cars. And so maybe I'll just pick on the Toyota Camry here. And so based on the shape of the car, there is this C value, this coefficient here. It's called the drag coefficient. And so this is the C. There's actually an extra factor of 1/2 thrown in there for reasons that you'll see when we do energy. So let me just say that you could have defined the shape without the factor of 1/2, but as you'll see when we talk about energy, the extra factor of 1/2 is very useful. Now, extra factor of 1/2 always bugs students. Why is that 1/2 there? And I understand why it bugs you. It's just like randomly thrown in there. But it's very useful, and it won't make sense why it's useful until we get to energy. Yeah.
When you're saying high density or low density, is that about the fluid or about the object?
The fluid. Thank you. Yeah, the fluid. Because this is the drag. This is the interaction of the fluid. Yeah. Okay, so the standard symbol for density is the Greek letter rho. I don't know if you've come across that one, but that would be, how much mass per volume. Cross-sectional area, well, this probably best is to use our capital A for area. We've already seen that symbol. And for fast-moving objects, I'll put V squared. So again, this will be our discussion for fast-moving objects. And basically, we like to say it's proportional to the square of the speed. How fast is it moving? Sadly, and you can see now why your author put this in the second chapter, doesn't that make it kind of hard to figure out what the velocity is? I mean, think about this ball that's falling. When you first let it go, it's barely moving. It's going slow. So how much drag do you have? Well, very little. I mean, we could roughly calculate these other ones because here's a half, and we can look up what this shape is for the ball. And so coming over here to the chart, I can go, okay, here's a sphere, and it's 0.45. Okay. So the shape comes into play. If I'm dropping it in the air, I can look up the density of air, which happens to be 1.21, so roughly at sea level. I can figure out the area of it. Of course, I'd have to tell you what size the ball is. But the trickier thing is then what speed is it going? Because at first, it has very little speed, but then it picks up speed. So then this gets bigger, then it picks up even more speed, and then it gets bigger, and then it picks up even more speed, and it gets bigger. Can we do a free body diagram here real quick? Here it is. Isn't this pulling it down and this lifting it up? Well, let me do something that I haven't been doing too often, and that is, let's call down positive. If I applied Newton's second law here, so the net force equals ma, and I looked at this, I would say down is mg, the drag friction, Fd, has to equal to ma. And if I'm using this equation for something moving fast, I guess it would become something like this. mg minus 1/2 times the coefficients times the density times the area times the speed squared equals to ma. Ooh. Now wait. Let's study this math for a moment. What is this saying if I just kind of think about it conceptually as its speed as time goes along? So at first, when I first drop it, its speed is 0. So if its speed is 0, I have absolutely no factor here. I just have mg equals ma, the m's cancel, and that then says that the acceleration is equal to g. Now, that's not a surprise, right? That's the acceleration we said any object would have if you dropped it without air resistance. And if it's not moving, it doesn't have any air resistance yet. Okay, so when I first drop it, it has an acceleration of g. In fact, maybe I'll give myself a little bit of room here and say I should maybe think in my mind about the acceleration. And so the acceleration versus time. And so it would start off up here at 9.8. So I'll put a little dot, and the speed would start down here at 0. And of course, because it has an acceleration, it would start to go faster. So on this graph, it would look like that. But see, notice that now as it goes faster, doesn't that mean it increases the air resistance? Which now you have its weight minus a little bit. So what is that going to say about the new acceleration now that it's moving? Do you see how the acceleration now would be a little bit less because you have some drag going on? And so the acceleration would maybe move down to here. And so instead of being 9.8, maybe it's only 9. Yeah.
Is there a reason why it's not negative?
Oh, yeah, just because I decided to call down positive and avoid negative numbers. So that's why I'm using a positive 9.8 instead of like all the other times I used a negative. Yeah. So I was thinking that was better. I guess I could do it with the negative value, but yeah. So I thought I'd just start thinking about down as being a positive. Oh, good. I think it's better this way, even though it's kind of reverse of what we've been doing. Now, I want to emphasize when it has an acceleration of 9, that of course still means it's going faster. It's just not going faster at the same rate. So maybe my velocity graph would kind of maybe arc over like that. But it would still go faster. And what I want you to see then is if it would go faster, that means this number would get bigger. So the air resistance is getting bigger and bigger and bigger and bigger. And every time the air resistance gets a little bit bigger, every time this gets a little bit bigger, I take its weight minus this number, I'm going to get less acceleration. And so maybe the acceleration goes down to 8. But of course 8 still means go faster. Now, not at the same rate, but it still says go faster. And of course, once it goes faster, then it has even less acceleration. And I'm hoping you're seeing this whole game here, that as it goes faster, 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 the air resistance becomes more and more and more and more, and it's getting closer and closer and closer, eventually getting close to its weight. What would happen if this air resistance was equal to this number? What would be its acceleration? 0. And so that's why I'm drawing a graph that would probably look something like this. It would start off with an acceleration of 9.8, and it would drop down and have less and less acceleration. And as the acceleration becomes less and less, the velocity keeps climbing at a smaller and smaller and smaller rate. But eventually, if you're willing to say, let's take the asymptotic limit so that the acceleration becomes 0, what would the speed become? A constant. And it would, on a graph, just kind of flatline right there. And that's referred to then as the terminal velocity. And so what we're hopefully seeing here as we take a deeper dive into friction and air resistance is now we see when objects fall out of the sky, they don't just continuously go faster and faster and faster. They eventually get to a point where they are going so fast that the air resistance lifting them up is equal to their weight down, and their net force is 0. And Newton's first law then says they will continue to move with that same velocity for the rest of the path. And that's an important difference, because now we can talk about more realistic things. We talked about dropping a ball and it going faster by 9.8 every second. And so if you drop the ball at the top of a mountain without air resistance, it would be going really fast. Even a raindrop coming out of a cloud at 10,000 feet would come down at thousands of miles an hour and kill everybody down on the ground. So luckily for all of us living things down here on the ground, there is such thing as a terminal speed. And that's what I'm getting at. This is eventually going to reach some maximum. For humans jumping out of an airplane, of course, as we talked about, it would kind of depend on how the human was positioning themselves. It would depend on that coefficient. In fact, I think they have it down here. They have a skydiver that is laying out flat horizontally. The coefficient is 1. Do they have a skydiver that's kind of tucking in and putting their head down and I guess they don't. There is a homework problem like that. Oh, is it here?
Yeah, feet first.
Oh, feet first. Okay, so they have feet first. So, okay, so feet first would be a little more aerodynamic than just flat out horizontal. And so you can see there's a difference in the coefficients. And then, of course, you can see there would be a difference in that terminal speed. In fact, how would I then solve this for the terminal speed? And I hope you're saying that the speed gets high enough so that that number equals that number. In other words, the acceleration is 0. So when mg minus 1/2 c rho a v squared, and I'll put a little t. So when we're at this terminal speed, your acceleration would be 0. So you see how I'm tying in Newton's second law from the last chapter here into this chapter, together, of course, with a deeper dive about what air resistance is? Now, if I rearrange this, I could leave the mg over here and put the 1/2 c rho a v t squared. I can then move the 2 over to here. I could also move the coefficient of friction or air resistance over here, the drag coefficient over to here. I can move the rho. I can move the area. And then finally, I will take the square root. If it's okay, do quite a bit of math there. Move it to one side, divide, and then square root. And so here would be the mathematical way of what I was trying to say conceptually. There is going to be some terminal speed for this human, for this baseball, for this water drop. Whatever it is falling out of the sky, it won't get any faster whether it falls 1,000 feet or 10,000 feet. Now, I guess at some point we might argue that you're getting so high that the density of the air changes, and that's a whole nother factor here that I won't go down that road. But I would say, notice then that feet first had a smaller coefficient than the horizontal position, and therefore, since it's in the denominator here, the smaller number is going to give you a higher terminal speed. And so you would be going faster feet first than if you were going spread out, horizontal, going down. Yeah.
So all like these like shapes, that's what we're looking at, right? So that would affect the velocity, like at terminal velocity, or the time it takes to get to the terminal?
Well, this is a calculation of the terminal velocity. Another question is asking, how long would it take to get to terminal velocity?
So that time is very specific to the shape.
Well, yeah.
Okay.
Yeah, because, and I'm not sure how far I should go with this, because this is harder, even though you guys know some calculus. If I were to change this to dv dt, I now have the ability to integrate both sides and solve for t, and that's what you're asking, how much time would it take to get to terminal velocity? That might be asking a little too much, so I'm not going to go down that road here for this class. So this is not saying anything about how much time does it take to get to terminal speed. It is just saying that it's going to, if it has enough time, or if enough distance, whichever word you want to put there, it won't go any faster than that. Now, since this is a life science class, this is extremely important, and I think for humans really hard to digest. Because we think, okay, if I was climbing in the redwoods and I was up on a tall branch at 300 feet and I fell off the tree, it's over, right? I'm going to come smashing to the ground and I won't survive that. But what if instead of being a human, I'm a mouse up there? A spider. What if I'm a little spider living on the end of this branch and big spider comes down the end? Like, okay, there's big spider, there's a 300-foot drop. What do I do? Do I stay here and fight the big spider? Or do I jump? Now, if you're a human, it's certain death. You might as well try to fight the big person. But if you're a spider, your terminal speed is so incredibly low that you're going to reach that speed within the first couple of feet. So it doesn't matter whether you're jumping 1 foot or 300 feet, you're going to fall at the same speed all the way down. And so for a little spider, and for things up to about the size of a mouse, their terminal speed is so low that jumping off of a cliff of 300 feet or a tree at 300 feet is not an issue. You know, you're a mouse on a branch and a snake comes at you, jump. you're going to hit hard, you're going to get your wind knocked out of you, but you're not even going to break a bone. You're going to walk away. I guess assuming you're not landing also on concrete down below, but if you're out in the forest, you're going to have some soft soil probably down below and a lot of organic stuff, and that's the way to go. So I like this book because your book goes a little more appropriate for this in the biology, and I think they quote some old scientists, and then that's what they get into when they first discover this, that hey, it's things that are about a mouse size and smaller, they view this world totally different than you and I, because they would survive, whereas a human, they say, would break and a horse would splat. And so there's a difference, and an important difference based on this terminal speed here. Now, the same logic, and so I'll just mention this kind of quickly, how would this be different if instead I was talking about something moving fast in a low density like air, if I was talking about something moving kind of slow in something thick? So maybe a ball bearing in water. Or maybe even a submarine in water. Or maybe more appropriate for you guys in the life science, how about some kind of bacterium moving through the water?
Would it be harder to reach terminally?
Yeah, and there's something very different here. There still would be a terminal speed here. And so let me illustrate by just changing colors. I guess I would still start off like this and say there's gravity pulling it down, and then there's the drag force. And so here's the first three lines would be the same, but this would be a little different. Remember we said it would be just related to velocity. Which means when we do the math for the terminal speed, there wouldn't be this square root. And your author gives it to you without proof, and I'm going to do the same thing. And so I'd say we're doing a kind of a deep dive, but not too deep of a dive. If you dropped a sphere, so I'm going to point out that the R then is a radius of a sphere. And this Greek letter is supposed to be eta, is called the viscosity. And here's where, I hope we don't cheat you too much, we just really don't have time. What is viscosity? Yeah, let me just say it's something that we use. It's a number we use to measure how well does something flow. Water flows pretty good, so we would say, hey, put water in a pitcher and pour it. It has a low viscosity. It flows really well. But pancake syrup, you make those pancakes and then you turn it upside down, you squeeze it, and it oozes out and kind of piles up on the pancakes, and then it slowly spreads out. It does flow, but very, very slowly. It's sticky. So we would say that has a high viscosity. So the viscosity is kind of that measurement of how well it flows. And you can see why that's important. If you're trying to move through this liquid, it's how much does it flow around you? So you can see that the viscosity does become an important factor, and so does the radius of it. And you can kind of see where the pi and the 6 come from, because as it moves through, the area of a sphere would have a pi r squared in it, and so there's the pi, and factor of 6 isn't so obvious, but hopefully the radius and the viscosity are, and the speed is. So again, without proof, your author just says, let's use this equation when we're talking about moving through a liquid. I don't know if you're familiar with that phrase, when somebody's really slow. Have you ever heard the phrase, you're as slow as molasses, because the viscosity of molasses is high. Or better still, you're as slow as molasses in January. I don't know if you've ever taken pancake syrup, but I know our maple syrup, it's pretty thick, so we always warm it up a little bit. I put a little water on the stove and put the maple syrup in there and then make the pancakes, and so then when you come out, it pours much better. And so the viscosity is temperature related. Now, maybe you've put oil in your car, you know, it's like in your car it says, oh, you need 10W30. And that W is the weight. It's a measure of the viscosity. And so it's a number from a 10 to a 30. And so when the engine is cold, it's got a lower viscosity because the temperature makes it higher and it makes up for it. And so it gives it a range here. Anyways, probably saying too much about viscosity. I just want to point out then, watch some of the problems, we're going to do this, and if we do the same logic, doesn't it still kind of say the same thing? That as you drop this BB in the water or in the maple syrup, isn't it going to go faster and faster and faster and faster? But at some point, this term right here equals that term. And so when that happens, you're going to have mg minus 6 pi r eta v equals 0. And that's what we call the terminal speed. So if you solve this for terminal speed, you would get mg over 6 pi radius eta. Moving it to the other side and then dividing. And so this is how I would get the terminal speed for a scenario such as a BB going through a liquid. In fact, as an engineering perspective, this is how you weigh the viscosity of the oils. And so if you were an engineer for Pennzoil oil, you would make the oil and you drop these little BBs in there and you measure their terminal speed. And then from that you calculate the viscosity. And then of course if you're a manufacturing engineer, you'd say, okay, we're trying to make 30 weight oil, so we need a certain viscosity, and then you add your elements to it and go, okay, this is too low of a viscosity or too high of a viscosity, but you can then check your batch and figure out what the viscosity is we're after, and eventually you get your 30 weight, and then you know, do all the things you need to figure out what the oil is. Well, like I said, I hope all that helps. Let's do an example or two. Maybe we get one or two done before the break here. You guys up for it? All right. So let me go to the end of the chapter here. And let me make it a little smaller here.
Oh, I had a question.
Yeah, fire away.
So with the diagram you showed earlier with static and kinetic,
Yeah.
so is kinetic always a result of static friction, no matter what? Because like with the diagram is like, okay, so the static builds up until its maximum, and then as a result you get kinetic friction.
So I wouldn't say as a result. I would say all of the frictions are a result of the rubbing of the molecules together. That's where it comes from. That graph was what you might call in a math class a parametric plot, where I wasn't saying one was dependent on the other. It wasn't like,
Comparison.
right, it was more of a comparison of how does this force, when it's static and kinetic, compare. Yeah. So so there wasn't a cause and effect. The cause and effect is the friction depends on them rubbing together. In fact, maybe a good visual picture of the cause and effect is this. When you are in a static situation, if these are the hills and valleys and these are the hills and valleys, they might kind of, in a static case, kind of, you put them on top and they kind of fall into place like this. And then when you push, the static force can increase because you're kind of rubbing the hills and the hills on this and the hilltops on this, they're kind of rubbing against each other. Eventually they break free, and then they just kind of skim over the top of each other. You know, like this. And so that's why then it's a lower value than when they were kind of locked in together, pushing on each other. And so the kinetic friction then will always become lower than the static. But the cause is those kind of the hills and valleys of the molecules locking together. Okay, so I'm just going to say, let's take this new information we have and apply it then to what we've been doing in chapter 4. That's really what this chapter is about. And number 7 is a good place to start. Looks like I went a little too high here. Let me start to the beginning of number 7 here and say, here it says, consider, and let me just, maybe to save a little time flipping back between the PDF, I'm going to get ready to look up some of these numbers in the table. So let me just open my hard copy to chapter 5 and say, okay, consider a 65 kilogram ice skater being pushed by 2 others as shown in the diagram below. So this is kind of an aerial shot looking down. Looks like this lady in the center is the one being pushed by these 2. So one of them's over here to her left and one of them is behind her, and there's a force 1 and a force 2. Okay? Find the direction and the magnitude of the total force, or let me just say net force, okay, because the combination of all the forces, exerted on her by the others, given that the magnitude of F1 and F2 are each 26.4 and 18.6 respectively. All right. I would say at this point, this has nothing to do yet with the new information. This is exactly more practice of putting together and solving Newton's laws equations, and so we have to get the net force. And so my comment is always, step 1, get a good physical picture of what's going on. And since the author has given us a physical picture, or physical picture of it, let me not do a physical picture. Let me skip over to step 2, which is the free body diagram. And so I'll just take and make a little dot for the system I am interested in. And so this is, again, a good chance for me to repeat what we did in chapter 4. Pick the object of interest. What are you trying to study? And we need to know all the external forces on that object. So the one we want to study is the woman in the center. Okay? And so that's what my dot represents. So then I want to know, well, what forces are on this woman? And from a top-down look, it looks like there are 2 forces from each of her friends. One to the left, and I guess they're friends. I don't think they're pushing her in a mean way. Okay, so I'll say her friends are giving her a little push. They're teaching her how to ice skate. All right, so the one to the left and the one behind her are helping her ice skate, and they're each going to give her a little push. Okay? And so in my free body diagram, it would look like this. And I'll flip this back to yesterday. Do you care if I put the arrowhead pointing out this way or pointing inward? Either way, it's in that direction. And I have a preference of drawing it like that. I know even though the woman on the left is actually pushing from her left side, she's pushing the woman to the right, and that's the F1. So in my diagram, let me put it this way as F1. So the tail is where the woman is. But again, these are not supposed to represent distance anyways. That's why it doesn't matter which way you push. It's just supposed to represent that we're pushing to the right. Then the woman behind her is pushing with a force number 2. And in my picture would be up, and their picture also. And let's see, what do we have? 26.4 for number 1. So 26.4 newtons for number 1. And it was 18 and change, 18.6 newtons for number 2. And it can get a little tedious, but I always encourage the free body diagram. It really helps get your thoughts into place. And notice then, we only have to focus on that one object. And so in this case, we can stop paying any attention to the two friends. They're not even in the diagram, because at this point it doesn't matter where the force comes from. There is a force, and that determines the motion of it. All right, so now we need to get the total, and since we're adding vectors, I'll just first write it as total equals the force from number 1 added to the force of number 2. And this is a pretty easy one because, again, as I like to say, you might want to make 2 columns so you can put x's with x's and y's with y's. And so if you take a look in this picture, it's almost too simple. How much force in the x direction do we get from number 1? And in this case, we don't have to do like a cosine of some angle. It's just all of it. All of force number 1 is in the x direction. And for the x direction of number 2, I would say 0, right? Number 2 is all y. And so when I add those together, I just say the total in the x direction is 26.4. And maybe that was so obvious you didn't even have to write out the 0 and add it together. The same is true in the y direction, that if I look at the y direction of number 1, there's going to be 0 force in the y direction from number 1. Number 1 is only pushing in the x. And in the y direction of number 2, it's all of it. And so when you add them together to get the total, again, maybe all that was unnecessary work. But I did want to remind you that's how we add vectors together, right? That you've got to take the x component of the 2 of them and add those, and then the y component of the 2 and add those. This one just happened to have zeros with them, so it was very easy to see and very easy to add, but they're not always quite that simple. All right, so since this is the 2 components of it, if I were to draw a picture of that, you're saying that the force in the x direction is 26.4, and in the y direction is 18.6. So this right here, the hypotenuse, would be its total. And so just like we did for velocities way back on chapter 3, we would apply Pythagorean theorem here in order to get the magnitude. So the magnitude of the total force squared would then be 26.4 squared and 18.6 squared. And then after a little bit of calculator work, we can answer what is that magnitude. So 26.4 squared plus 18.6 squared, enter, and square root. And we're looking at about a 32.3 newtons. And as we've said many times, when you're dealing with vectors, it's a bit challenging because you got to remember they're components. And so what you're really saying is one push plus the other. You don't just add them together. You would get a number much bigger than 32. But because of their direction, those 2 are equivalent of one force with a push of 32.3. And in terms of the direction, theta, I could then say, all right, tangent of theta is the opposite, 18.6 over 26.4. And so now I can say, okay, what is the angle here? So I'm going to go inverse tangent of 18.6 over 26.4, and I get 35.2 degrees. And I think I've answered A, although I must admit this was a good review of chapter 4, not so much anything new here in chapter 5, but I think that will change here. All right, so the total force exerted on the others are, okay, respectively. Okay, so I found the direction and the magnitude. B, what is her initial acceleration if she is initially stationary and wearing steel bladed skates that are pointing in the direction of the force. Yeah.
I have kind of like a general question about like the cosine, tangent, and stuff. Is which one of those that you use like just dependent on which two values of the triangle you have?
Absolutely, absolutely. So I picked tangent for this one because I knew the opposite and the adjacent, and that's the tangent function. Now, technically, I could have put over here 32.3, and I could argue that I knew opposite and hypotenuse, so I could have done the sine. But I could have also used cosine because I know adjacent and hypotenuse.
Oh, so that's why sometimes you use like different ones for this.
Right. And so if I only know two of them, then I'm locked in to only one trig function. In this case, by the time after I got this, I knew all three, so I could use any of the trig functions to find the angle.
Okay.
And I just picked tangent.
Point in this class when we'll have to change the calculator to radians, or is it always?
No, we got to use radians too.
Oh, we do.
Oh yeah.
But like
Yeah.
so far.
Sometime in the same problem. Oh.
Really? Okay.
No, I don't think we'll quite go that far.
But so far we just use degrees, right?
So far we've used degrees, but I'm glad you asked that because before today's over, it will hopefully start 6, and the first thing they do is talk about angles and radians, and there's a reason why.
Okay.
So there's nice reasons to use radians, and there's nice reasons to use degrees. So we use both. I guess it's a little bit like saying it's kind of nice to sometimes measure things in kilometers, but it's also nice to sometimes measure things in miles. So we do both. And it's not just to see students struggle. That's just an added bonus. Yeah. I'm joking. Because it does happen. But there are advantages, so to it. But for the most part, in a science class, we always stick to the metric system. However, when it comes to angles, even in a science system and an engineering system, there's so much an advantage of using degrees and so much of an advantage using radians at the right time. We constantly use both. But that's to come. Okay, so let's come back over to here. And I hope you caught this, that they're asking for her, what does it say here? What is her acceleration if she is initially stationary and wearing steel bladed skates that point in the direction. And so this is really what this discussion was about. Wouldn't there be some friction then between the skates and the ice? And so let me kind of redo my free body diagram and say, all right, well, what I have is really, well, I'll say I have two forces from her two friends, but as we just said, that is equivalent to being pushed at 32.3 newtons. But as she stands there on the ice, wouldn't there then be some friction? And so here's my question. Would that friction be kinetic or static? Well, good. And it is a kind of a tricky question because it's like this block over here that if the amount I pull is less than the maximum static friction, the acceleration is going to be 0, they're not going to move. But if it is greater than the maximum, then she will move, she will have an acceleration, and she will be sliding, and it will be kinetic friction. So the first step of this is to ask the question, is this force enough to overcome the static friction? What is the maximum static friction? So I'm going to begin by saying the maximum static friction is the coefficient of static friction times the normal. That's our new piece of the puzzle. And I'll say it again, if this number is lower than this, she'll start to move. And it probably is, given that she's on ice. I think that's why they set it up this way. She's on ice skates. That's the fun part about ice skates. There's very little friction. You can glide and coast. And so I would be surprised if this was not enough to actually make her move. Okay? So we're going to need two things. We're going to need, first of all, this coefficient. So without changing my PDF here, I'm going to go back to table 1 here. I'm going to scan down here, and somewhere here it said still on ice. And so still on ice has a coefficient of static friction of 0.4. and a coefficient of kinetic friction of 0.02. So it's a big change, which is kind of nice. I mean, you can kind of stand there, kind of walk around. You can actually move and walk on ice skates. But then once you start gliding on them, once you start sliding, there's actually very little friction. And so that's the neat thing about still on ice. Now, to get the normal force, maybe I better change my free body diagram from looking down to looking to the side. So again, I'm a terrible artist. So he'll be my ice skater. Here's the woman we're focused on. I'll even put some silly looking ice skates on her. So here's my ice skates. And here's the ice. And if I do a free body diagram, I would say her weight is pulling her down. The normal force from the ice is lifting up. Maybe I'll come over here and say, let me add up all the forces in the y direction and set it equal to mass times acceleration in the y direction. So I'll say normal force is up, her weight is down. Here's a fun one. What is her acceleration in the up and down direction? See how her friends push her horizontally? And we don't know that acceleration. That's what we're being asked for. But we do know her acceleration up and down. What's that? 0. Does she move up or down? No. And so, again, visual picture is absolutely crucial here. Right? This comes back to our first step. Did you get a good visual picture of what was going on? Because this diagram, I think, doesn't show it well enough as a 3D. This diagram shows as looking top down. But now if you change it, so like you were on the ice next to her, then that's what I'm doing over here in this picture. And I'm talking about what is her motion up and down. Whereas the question is, what is her motion horizontally? See how those are two different accelerations, right? That's why we made a big deal with it in projectile motion, right? Projectile motion, we had a horizontal in the x and a horizontal, we had a horizontal acceleration and we had a vertical acceleration. And I'm kind of saying the same thing here. And I'm trying to get you to see here that we actually do know, based on the physical picture, what the acceleration is of that individual. That individual is not like jumping up or crashing through the ice. It's going horizontally. And so what that means is the normal force is equal to the weight. Remember I said normal force doesn't always equal the weight, but a lot of times it does. And you can see when it does, you can see if there weren't any other forces and if the acceleration is 0, the normal force will come out to be the weight. And those are the easiest cases. They're not all the cases. But I'll say it again, if you don't have other forces, and if you don't have an acceleration in the vertical direction, then the normal force is the weight. And that's what we have in this problem. And so they even gave the mass earlier on, there it is, a 65 kilogram person. So I can come over here and say, all right, let's calculate this maximum static friction. The coefficient is 0.4. The normal force is the 65 kilograms times 9.8 meters per second squared. And so that needs to be my first calculation. Do I even have enough force for her to move? So 65 times 9.8 times 0.4 is 254.8. Whoa. That was a lot more than I gave it credit for. Did I do that right? Did I look this up right? Still a nice 0.4, yeah. Forgive me, I'm going to do this one again. 0.4 times 65 times 9.8. All right. So this is not enough to overcome static friction. They're going to be stuck there. Yeah.
Why were you using 9.8?
For her normal force, her normal force is equal her weight, mg.
I thought that was Newton's.
Oh yeah, good point. Yeah. So this n is for the quantity normal force, but of course it has the same symbol for as Newton's. Yeah. Makes me wonder about this problem. I see. Now it makes more sense. So I would say she doesn't move. This would, again, be like this example. Remember, to overcome the friction, I need about 10. So if I were only pulling at, say, 4, it doesn't move. It's not enough to overcome.
Maybe I'm not seeing it, but I'm wondering how you came to that conclusion that that number value wasn't enough to overcome.
Okay, so maybe I should write it with a graph again, and also with an equation that says the static friction can be up to its maximum. And this is its maximum. So, if I come over here, and if I pull with 1, the friction goes back at 1. If I pull with 2, the friction goes back at 2. This keeps going on until I get to the maximum, then it starts to slide. So here's what I would say. The maximum is over 250. So her two friends, which are pushing her at 3.2, mean that she's not going to move, so the friction is going to come out to be 32.3. I'm not saying this is the amount of friction. I'm saying the friction can go up to that value, and it could be appropriate to keep her from moving. And so her friends push her at 32, but then the friction pulls her back at 32, and so their friends are just going like this. They've got a little pressure on her, but she's not moving. And if they push a little harder so that they're pushing at 100, the friction will increase to 100. Eventually, though, the friends will probably push her more than 250, and she'll start to move. Yeah.
So is 254, what value is that?
So 254 is the most the friction can be. On this graph, the static friction can go up to 254. And they're what?
So it's the units is meters?
Yeah, and all forces are in newtons.
So it's an Fs max. It's like, what is the value of Fs? You know, it's
Yeah, max. So this is the, I should put Fs max.
okay. What would does it give you? The Fs is, what is the value of Fs?
So Fs maximum
It's 250.
is this calculation.
Yeah, but then what is the regular F?
So the regular F is whatever it actually is pulling back at, which has to be less than 254.
That's the 32.
Right. So that's why I'm saying the friction at this point would be 32. Because the net force has to be 0. Her friends are pushing her at 32, so the friction has to be 32. This would be the same as coming over here to this block and saying, I am pulling with a 4, the friction is 4. If I pull a little bit more, I'm pulling with 6, and the friction is 6. So the friction keeps getting more and more and more until it gets to the maximum.
Is it correct to think about it as like that 254.8 is kind of like the threshold between like the static friction and the kinetic friction, and so like once they push with at least that amount, she starts moving, and then the static friction turns into kinetic?
Yes.
Okay.
Yeah, that would be a good way of saying it.
So you would need an Fs value of like 255, in which upon any force she would move.
Right.
Okay.
Right. See, as I told you, this is why the the frictional forces are a little tougher, because you got to kind of stop and ask, what are we dealing with? Are we dealing with static or are we dealing with kinetic? And the static is the hardest one because it's not a set value. It can be any value up to its maximum. So I like to stop and just say, okay, was this enough to actually make her move? And maybe now the next question, we'll take our break before we even do the part C, but let's read part C, because look at this. I think part C helps us understand what we just got, because part C then says, what is her accelerating, assuming she has already been moving? So in other words, she already has a little bit of motion. That would then tell me that somewhere earlier she got enough to get started, but now her friends push her while she's slightly moving, and then that means I should be using kinetic friction, which is a much lower number. And we'll do that when we come back for the break. All right, so let's take a break, come back at 5 till, and we'll see you guys online soon too. Bye. Good. Hey, all right. Hey, everybody, welcome back here from the break. Let's keep working on this problem, and I discovered a little typo, which makes total sense now that I think about it. Let's keep doing this problem, but let's backstep for a moment. Everything we did was technically correct, but there was a little typo in the hard cover, or the hard copy of my book. Remember, I looked up and said the coefficient of static friction between steel and ice was 0.4, and the number was big and bothering me, and it's still bothering me. I'm going to look again. Yeah, it still says 0.4. However, that made me come over here to the PDF, and the PDF says it's 0.04. And that makes a lot more sense, especially when you compare it to the two above it where it says what would be the friction between your shoes on the ice. And you would expect it to be lower than that one, not higher. So let's come back over here and readdress this one and just say, okay, before the break, if the coefficient of friction was 0.4, like maybe she was, instead of on ice skates, maybe she was wearing cleats and she like dug into the ice, then the push from her friends is not enough. She doesn't move. But that's a lot of static friction, and that's why it came out to say she's not moving and not even close. So let's try this again and let's use the better number, and we'll see that she does move. And I think that was the author's intent. So let me come over here, and maybe just by changing the color, I'm going to change this to 0.04. That's a factor of 10, so that makes the decimal move over 1, and so that means her maximum static friction would be 25.48. And remember, her friends are pushing her at 32. That is more than the maximum. And so she is going to start moving. And so that's the difference. Oh, did I turn on my sound? Yeah. So that's the difference then between that factor of 10. So I would say now she is going to move. And so now, instead of just saying the acceleration is 0, she doesn't move, we can actually get a number here. And that number, I guess, would look something like this. If we then add up all the forces in the x direction, and if it'll be okay with you, I'm going to do something kind of weird for the x direction. I'm going to say, let's just call that the x direction. Otherwise, if I do a regular grid that's not kind of angled like this, I would have x and y components, and then I would have to find a two-dimensional problem instead of a one-dimensional problem. So if I make this the x-axis and I add up all the forces, I would say the 32.3 newtons is the force, and I should say the resulting force of her two friends. So this is force from her friends. And now, at that moment, and I think this is what the author is trying to say, at the moment she starts to move, the friction is at its maximum static, and eventually it's going to then drop down. But for just that moment, and I'll come back to here, this is kind of what they're saying. So it's at its maximum, so right here, and I think my maximum was about a 10, right? So bigger. So right at, oh, there's 11, 12. Oh, and there it moves. But right there, that first movement, before it drops down to the lower kinetic friction, is what I think the author is trying to say. And so I'm going to say her friction is negative 25.48. And then this is going back to chapter 4, Newton's second law. Add up all the forces and set it equal to ma. All right. And of course, we know that her mass is 65. So grabbing my calculator, I can go 32.3 minus 25.48, then divide that by 65, and we're looking at an acceleration of 0.105 meters per second squared. So that would be her kind of a initial acceleration as her friends push her. But of course, this is where part C comes into play, because as soon as she started to move, as you saw this one, it would drop away from its maximum down to its kinetic friction. So we probably need to do a new calculation for its kinetic friction. And that's how they worded the problem. I'll go back to the problem, but let me just remember this. I'm afraid to look at the hard copy one. It's going to mess me up here. Okay, but so 0.02, so it's half as much. I'll remember it's half as much here for the kinetic one. And let me go back to the problem. I believe this was problem 7.
So with the old version, with like if you were like cleats in ice,
Yeah.
then that means the initial would be 0.
Right. I would say there wasn't enough to overcome. So to answer the question, I would say 0 acceleration. Mm-hmm. Yeah. Yeah, and then that's what I was trying to say before the break. I go, well, it's 0. I don't have to calculate anything. It just wasn't enough to overcome the static one, so acceleration 0. But redoing the numbers, now we see it is enough, and it gives a small acceleration. So with that in mind here, this is why C comes into play. It says, what is their acceleration assuming she is already moving in that direction? Or put another way is, once she starts moving, then it's going to change to kinetic friction. So what I would do then is I would, and maybe just to make it stand out, I'll do a different color here. I would say then, what is the kinetic friction? And that's the coefficient of kinetic friction times the normal. And if you remember, it's half as much, so I can just cut this in half. So let's see. Half of 25 is 12 and a half. And half of 48 is 24. So maybe I could, if I don't mess up again here, do that in my head. All right, so there is the static friction. So when I come over here to part C, I'm going to do the same logic. Let's add up all the forces in the x direction and set it equal to ma. And in this case, then, I still have the 32.3 newtons from her friends, but now the friction is a smaller number of negative 12.74 newtons. That has to equal to ma, where m is still the 65, and so I'll get a difference. Acceleration and a greater acceleration because of less friction. So 32.3 minus 12.74, each divided by 65, and I get an acceleration of 0.3. Which, by the way, notice how the acceleration quickly changed, right? It was a small number and then it went way up. It kind of has a jerky effect. That's why it's always kind of hard to push somebody who's learning to skate. You give them a little push, once they start moving, then it changes. They're like, whoa. They're already trying to learn to skate and having a time balance, and then just nature adds to it, which is actually kind of the fun thing to watch. But anyways, but it was like, whoa. And you saw that here. Right? You see that when I pull it, I pull, and as soon as it breaks free, so it has a small acceleration and then quickly goes to a large one, and it kind of has a little jerk effect to it. Okay? And of course, it's even more complicated because then my hand kind of responds. I went, whoa, yeah. You can get it more complicated motion. All right, well, that was actually a pretty deep one and maybe a little hard to start off, but let's do 8 and 9. 8 really is kind of leading up to number 9. You'll see here 8 doesn't have any of the new stuff. So this will be, this first one, 8, is really good for reviewing chapter 4, and I know you guys are still kind of working and struggling along, learning how to do the Newton's laws. And then let's add to that with number 9 here. All right, so let me clear the board. Maybe I'll wait to clear the rest of that. Let me find a black pen. Let me put number 8 here and read that together. So number 8 says, and this will be a good time for me to pause again and say, would you like to know all the answers to all the homework problems for chapters 4, 5, and 6? Did you see how I just kind of wrote out the forces and set it equal to ma? I keep doing that. And again, I know that's kind of overly simplifying it, but I just want to take that moment and say, that's what I did. Now I'm just doing a deeper dive into frictional forces. And so we're going to look at all those. Well, like I said, number 8 doesn't have frictional forces yet. Number 8 is a build-up to number 9. So number 8 says, show that the acceleration of any object down a frictionless, see, there it is, that's really no friction, so kind of back to chapter 4. A frictionless incline that makes an angle of theta with the horizontal is given by A equals G sine theta. Okay. So let's come over here and step 1, draw a physical picture of what's going on. So I'm going to make an incline in my picture, angle theta. I'm going to put an object on the incline. I'll just put a little block here, keep it simple, and say if I let go of that block, it's going to slide down the incline. Especially if it doesn't have any friction. I know you might be asking, well, it may or may not slide, but if it doesn't slide, that's because it has friction. And this problem is without any friction, so it will definitely slide on this part. If we have friction, well, that's kind of the next part, 9, is will it actually slide? But let's just say again, without friction, this is going to go down the incline. All right, so step 1. You good with there? Step 1, got a good physical picture of what's going on? Okay, step 2, free body diagram. Okay, so free body diagram says take the object that you're interested in and draw only it, or just make a little dot for it. Because the real point then is to label all the forces on that object. And I like to say it's everything touching it plus the weight. All right, let me start with the plus the weight. So in this free body diagram, I'm going to draw an arrowhead straight down. I will call it W for weight, but we know that equals to mg. All right, so there's our chapter 4 stuff. Now, in terms of touching it, the only thing touching it is that incline. And as we said, with the incline, when you put something on a surface, there would be a normal force. There also, if there is roughness to it, friction in a horizontal direction. So a surface can have those two components. It can have a normal and friction. But this problem, remember, no friction. So I won't worry about a friction on the surface. It's just going to be a normal. Maybe the one thing that makes this problem hard is which way is the normal? Let me say it again. Perpendicular to the surface. Right? That's why we call it a normal. We're taking that word from math. I don't know, like I said, if you use that in your math classes, but it's a common word. It's for a line that is perpendicular to a surface. All right. So here is our normal force. And that's it. Those are the only two forces. Okay? Now, just to help me with my thinking, and so I'll do it in kind of a different color here. Maybe I'll do some red. My green's getting kind of dry. We don't usually put other things in our free body diagram, but I'm going to put a little dotted line in red to show what direction the object would actually move. Fair enough? Moves down the hill. So remember, this problem is asking for the acceleration, and I have a question for you that I will help you answer. But in order for me to figure out the acceleration, I need to put a grid on here. In fact, maybe I should pause and say, okay, I'm done with step 2. I've done all the forces. Now I want to go to step 3. I want to write out the equations. And to write out the equation, I need a grid. My question for you, should I use a traditional grid where X is horizontal and Y is vertical? Which, let's talk about the pros and cons here. The pros would be, well, I'm used to that one. That's the traditional one. I feel more comfortable with that one. I'm having enough trouble with the math. Don't throw more at me. I like that one. All right, so I would say there's a real positive about that grid. but there's a huge negative. What direction does it move? Notice how it doesn't move along an x or a y axis. Notice then, if we use that grid, we're going to have to figure out what the acceleration is in the x and the acceleration is in the y, and then do the Pythagorean theorem and go x squared plus y squared equals the hypotenuse squared. Fair enough? Now that's not so bad, and if you're comfortable with that, fine. But I got something that I like a lot better, and when you get comfortable with it, you're going to prefer. What if I did a grid in the orange that down the incline is the x and perpendicular to the x is the y, and so kind of a tilted one. And now again, let's talk about the pros and cons here. The bad thing, the con, would be I don't like the looks of that. I haven't done that before. But let's talk about the pros. Notice that this object would only move in the x-axis. So if you found the acceleration in the x, you're done. There's no x squared plus y squared equals hypotenuse squared. Also notice, what would be the acceleration in the y direction for this orange grid? It would be 0. It would be our discussion about the woman on the ice skates. It's not going up or down. So the good thing about this is I don't have to worry too much about the components of the acceleration. Not at all, in fact. And I don't have to, and I do know the acceleration in the y direction. And I claim that that's so much better. So let's solve this with a tilted axis. Because I'm sure for many of you, maybe even all of you, it's the first time you did the problem with a tilted axis. But my comment is, if you ever know the direction of the acceleration of it, if you put your axis in that direction, it's so much easier. Because now the acceleration is only x, and in the y is 0. And remember, that goes into your equation. Acceleration in y is 0. Isn't it so much nicer to have math equations that have a bunch of zeros in them? So this can be a powerful tool to get away from the traditional axis and tilt it, and you just have to think about a tilted axis. Now, yeah.
So, I agree that doing it the way you just said is the better way, but I'm just asking, if we did it the old way, what vector would we be solving for?
So you'd be solving for vector A, because it asks for acceleration. So you would get first an acceleration in the x, then you'd get an acceleration in y. And in this case, then because they have the angle and then we don't have numbers, we would have like sines and cosines, and then we would square them. And then we'd have to do a trig identity. It's very messy to do this without tilting your axis. So I'm going to tilt the axis. And the math is so much easier. Like I said, a little uncomfortable at first, but so much better. All right, so with the tilted axis, so I'll go ahead and continue with the orange color. Let me make a little table here that has x over here and y over here. And let's write out the equations. So this is what I say about step 3. Step 3 is to write out the equation. And I already said something very useful over here, and that is that the sum of these vertical forces, which equals the acceleration in the vertical direction would be 0. Now in this problem, you'll see that because friction is not part of it, the y one is unnecessary. But I want to put it on there because, again, the point of me doing number 8 is so I can follow it up with number 9. But let's look at our forces, say, in the x direction. And I've kind of covered them up. I hope you can still see them in the black. This normal force is all in the y direction, nothing in the x. So when it says add up all the forces in the x, nothing from the normal force would go there. In fact, as long as I'm mentioning it, maybe I should put it here and say normal force N. I would say that's the other benefit of this tilted axis. It makes finding the components of the normal force really easy. They're all y and no x. However, there is a price to pay. When you tilt the axis, notice weight is no longer in the negative y direction. Now let me say that again, because I want to emphasize the weight is still down. It's just down is not the negative y axis. So that is the sad piece of tilting our axis. So pros and cons. But this is not a real negative or a real big con, but we probably want to think about it here. All right, so I'm going to do this. I'm going to have you imagine my arms be the x-axis, and my head and body is the traditional y-axis. So vertical, horizontal, and now I'm going to tilt. See, I am trying to tilt by an angle of theta. Or maybe I'll draw a horizontal here, right? If the slope of the hill is theta, then I'm trying to tilt my x-axis by theta. Now the reason that's important is I'm going to draw, and maybe I should do it in orange, the negative x-axis. Because this then would also be theta. See, if I tilt the x-axis down by theta, doesn't that mean I tilt the vertical negative y-axis by theta? And so that's why I'm trying to give you visually something to look at. Tilt by theta. Because if I try to break down the components of the weight, I'm going to make a little triangle right here. So this is the amount of weight on the y-axis, and this is the amount of weight on the x-axis. So there's the negative piece, right? The negative piece by tilting our axis is we no longer have the weight on the y-axis. We have it off axis, and so we have to look at its components. But fortunately, if you visualize that tilt, you can say that the y component is cosine of theta because it's adjacent to the theta, and the opposite component is sine theta. So here's where I'm going to come over here and be able to answer this question. What is the amount of force in the x direction from its weight? Well, its weight is mg, and the part on the x-axis is cosine theta. That's this piece right here. So look at this triangle. This is the hypotenuse. This is the weight of it. And I want opposite, that's why I did sine, of it. And that's the only x component. That's what makes it so easy. Remember, we tilted it, so the normal force was only in the y. That is the only piece in the x-axis, right there. Now, if I look at the y-axis, I could say this would be mg cosine theta. So let me say it again. This is step 3. I'm writing out the equations. And part of writing out these equations, of course, is picking what grid. So I picked this orange grid that was kind of tilted. And like I said, what's nice about it is once I tilt it, over here on the y-axis, the acceleration is 0 and the normal force is only on the y-axis. The sad part about tilting it is now the weight, mg, is not on either an x or a y-axis, so it has an x component and a y component. The y component is in the negative direction, so I'll put a negative, and the x component is in a positive. Okay. Now let me take one more step with step 3, and that is to put down the accelerations. And in fact, here was the big point of this grid. I don't need to put a sub x here anymore. There is no acceleration in the y direction. This sub x is the total acceleration. And now you can see we solved it. Step 4, solve. Cross out the m, and you would say the acceleration, and I'll just say total, I won't even bother to say x component, equals to g sine theta. And that's what this problem was telling us to do. Can you prove that the acceleration down a hill is g times sine of the angle? Now, we weren't asked to do anything about the normal force. We only need normal force when there's friction. And that's what this chapter is about. So let me go ahead and do step 4 for the y direction. Let me solve for normal force. And let me also point out, notice normal force does not equal mg. So again, don't think that the normal force always equals the weight. Remember I said it would only equal the weight if there weren't other forces and it wasn't accelerating? This one's accelerating down the hill. So it doesn't come out to be mg. Mm-hmm. And maybe this is worth repeating those 4 steps. Step 1, good physical picture of what's going on. Step 2, draw the forces. Step 3, write out the equations. And there was the big one for this problem. When it came to write out the equations, that involved what kind of axes, what kind of grid. And I twisted it so that then step 4, solving it, was just a quick step. Otherwise, I would have had all these trig identities. I would have had sine squareds and cosine squareds, and it would have been a nightmare. And so I saved myself a ton of math because of the right grid. Yeah.
So there's no, like, in the y direction, you do n minus mg's because the normal force is opposing the weight. In the x direction, there's nothing opposing the mg.
Okay, so
You know, it's like the summation.
So this piece and this piece each come from the weight.
Yeah.
All right. And so this is the weight like this. So on your grid, your XY grid, think of this as being to the right and down. So to the right is positive, down is negative.
But so the y only has the n though, because.
Oh yeah, and then the n right here is only in the y direction. Yeah,
Okay.
yeah, yeah. It's just all along the y-axis, and that was a benefit of tilting the axis.
Could you explain your picture again? Because I understand that we needed like sine and cosine because of the tilting.
Yeah.
But I didn't understand
So yeah, let me clean up that picture a little bit. So let me make a tilted X, Y grid. Let me put a black line straight down representing the weight, which is equal to mg. Let me mentally just kind of go through this tilting of my head again. So this angle is the theta, not that one.
So, what happened to the incline? Where's this?
So the incline is along this direction of the x. And so I was going to say, I guess I'm not drawing the incline, although I could kind of say I am drawing the incline because the incline is the x-axis now. That was the whole reason of saying I'm going to take a grid like this and then I'm going to tilt it so it looks like this, down the incline. But I think if I understand your question, you're asking, how did I get this in the y direction and how did I get this in the x direction?
I think I'm just having trouble seeing where the angle is because we are like this, and then the angle goes like this, but then now you're looking at the angle on this side instead of.
Okay, fair enough. So here's what I'm going to say. Let me redraw the incline. The definition of the incline is that one, theta. Why don't I draw the traditional grid at the top of my incline for just a second? And I'm going to take advantage of a little geometry. They're called alternate interior angles, and point out that that would be theta also, because I'd have two parallel lines cut with a transit, and those are alternate interior angles. So if that's theta, that's theta. Okay. And what I'm going to do then is imagine taking this x-axis and twisting it so the x-axis is now along the incline. So I want you to imagine I'm twisting it by theta. So if I twist the x one by theta, then this y would twist over by theta.
I think I understand now. I think I was confused on how it went from this side to going up there, but now that you explained the parallel incline.
Good. Yeah. And this always goes with I'm helping students. It's we call it physics because it's about the physical world, and you got to see these pictures. Yeah, you got to see them in your head, and that's a skill. It takes a while to develop, and that's I guess what my goal is to get you to develop that skill, and it's very much harder in the summer because that's a skill that just takes a while to digest. And our summer pace is so fast, you don't have that. Yeah. Okay, so I'm glad you see that, but I finally got to this answer and even got a little more than they needed to do for this problem, but it'll set me up for the next problem. Let's try the next one here. And so we're going to repeat this and say, okay, show that the acceleration of any object down an incline where the friction behaves simply as kinetic friction is given by this equation. So shall we repeat all this but now have friction? All right. So if you'll let me, I will maybe just start off with a clean slate. It'll be good to see this a second time. In that one, I'm going to change that to a 9 and say, let's give this a try. Let's try to go through all these same 4 steps, but I'm going to include now friction. All right, so step one might be to say, all right, I'm going to do problem 9. I'm going to get a good physical picture of what's going on. So I'm going to draw my incline at angle theta. I'm going to put my objects on the incline. And I'm going to say that it does start to move. I know it kind of is questionable because this one has friction. But since they say go ahead and give this as the acceleration when it has kinetic friction, I'm going to assume that it's tilted enough or the friction is low enough that it'll actually start to move. And so I'll stop there. That's step 1. Got a good physical picture of what's going on. Because step 2, free body diagram, is to say take this object and draw all the forces on it. This goes back to what I said. The forces would be weight and everything touching it. So the weight would be mg. What's touching it is still the incline, so there would be a normal. That looks like what we just did. Then there would be one more thing. There would be friction. Friction would be the opposite of the way it is sliding. It's sliding down the hill. So which way would the friction be? Up the incline. All right. So that's where our problem now begins a little bit different than the last one. Now, I would say I'm done with step 2. I've got the free body diagram, and I'm ready to head over here, and I'll do orange again, and say step 3, let's write out the equations. And when we start to write out that equation, we have to say what grid do we want. And I would argue on this one, the same as last one, that there are advantages and disadvantages of using the traditional and advantages and disadvantages of tilting it. And the advantages of the tilted one so outweigh not tilting it. Let's tilt it again. So, in orange, I'm going to draw on here, and maybe this time so I don't cover up the normal vector, I'll just draw the y-axis really close to it. And I'll even make the negative y-axis go over to here. And the x-axis is down the incline. That's why I'm tilting it, so the motion is along the x-axis. And notice then the negative x-axis is the direction of the frictional force. Okay, so picking that grid, I can then write out the equations. So I'm going to say the sum of the forces in the x direction equal mass times the acceleration in the x direction. And even though I call it the x direction, the reason for me to tilt the axis is because that is the total acceleration. I don't have to get an x and a y and then do Pythagorean's theorem. That's the part that would make a problem like this really hard, because we would have sines and cosines and then we would square them, and to make sines into a cosine we'd have to do trig identities, and the math would be hard. And we can avoid all that math if we just tilt our axis. Yeah.
When you tilt the axis, I think I'm just a little bit confused as to why you put friction on that side as opposed to kind of like under, like paralleling as opposed to the left side, like underneath, because you know how if it were to be sliding down but upwards.
Okay, in that case, whether I put the friction under the box
Will that change anything?
doesn't change anything. It's the direction of the friction that's important in this picture. And it kind of goes back to, sometimes I put a force towards the object, and then sometimes I put it away from the object. But as long as it's pointing in the same direction, that's all that matters in the picture. So I probably should have done it like you suggest, under the box, because that's really where the friction is happening. But this diagram, keep in mind, is not a diagram of position. It's a diagram of forces. And those are different vectors. So there's nothing in this diagram that is supposed to indicate position. Just directions. So that's why it never matters where you draw the arrowhead, because we're not trying to represent a position of the force. We're trying to represent a direction of the force. Okay. So, where was I? Oh, yeah. So I was saying we're going to write out these equations, and like I said, then we're going to solve for this A. And this A then is the total acceleration. Now, if I come over here and say, let's add up all the forces in the y direction, set it equal to mass times acceleration. I'm going to ask the same question. What's the acceleration in the y direction? 0. All right. Now, let's start writing them out again. And maybe I'll just go around and do all three forces like we did last time. I'll start with the two we did first. So I'll start with the normal force. How much of the normal force is in the x direction? None. Maybe last time I should have put a 0 there. How much of the normal force is in the y direction? All of it. Okay, so there's the x and y components of the normal force. Same thing here for the weight. This was that harder one. As you asked a great question, this would be the angle theta in here. So if we made a triangle, this triangle, these blue pieces would be the components of it. And so the cosine, that is adjacent to theta, would be the y-axis. And opposite of theta would be the x-axis. So that means how much of the weight is in the x direction would be mg sine theta. That's what we got before. And how much of the weight would be in the y direction would be mg, and it would be adjacent to the angle, so it would be cosine theta, and it would be negative. So far I've got the same thing that we got without friction. The only new piece is right here is the force of friction. Okay, let me ask, how much of the friction is in the x direction and how much is in the y direction? Again, maybe you can see advantage of tilting the axis. Isn't all of it in the negative x direction and none of it in the y direction? So I'll put plus 0 for none of it in the y direction. And over here, I'll put minus coefficient of friction times normal. And again, continuing on step 3, and that's writing out the equations, okay? I've now added up all the forces in the x direction, and that has to equal ma. And I'm just going to drop the sub x because this is the total acceleration. And over here on this side of the equation, what does it say? Acceleration in the y direction would be 0. All right, so keep in mind my goal, like before, is to solve for this a. But what's very different in this problem is I have normal force. I didn't have that last time in the x-axis. So why don't I solve for normal force here and substitute it in over there. Okay, so this would say normal force is mg cosine theta. And again, that's the same thing we got before. And I'm going to put it in here. So this would be mg sine theta minus coefficient of friction times normal force mg cosine theta equals ma. And maybe I should have pointed out, now I'm into step 4, the last step, solve it. So I solve for the y and put it over here. Divide everything by m, and then we're there. A equals g sine theta minus mu k g cosine theta. And I hope that's what they were asking. Oh, they factored a g out. But that's g sine theta, and then that is mu g, so maybe I'll make their last step. Take a g out of each term, and then you're going to have sine theta minus mu k cosine theta. Yay! Easy? Hard? Too much? Draw that free body diagram. Pick your grid. Write out your equations. Solve. Would you like to know the answer to all the homework problems? Right? And so in both of these, notice that's what I did. They got hard, obviously, with all the math and breaking apart the components, but it still is the same logic. The logic is hopefully simple, and I keep saying that. Physics is about knowing how to apply a few powerful fundamental concepts to explain a universe of phenomena. So I can work out now the motion of any object with friction, without friction, a lot of friction, a little friction, a drag force. The list goes on and on. All I gotta do is write out the forces and set it equal to ma and solve. Of course, it sounds so easy, solve. Well, you know how hard the math can get and the trigonometry can get. Which axis to pick. So there's a lot of details in there. All right, well, bummer. I wanted to show you more here, but let's see where I can do maybe a little different one here, and we'll wrap up today here. 22 was the next one on my list, and I think this is now getting to some drag or air friction ones instead of what we just did, which was the solids to solid frictions. And let's try number 22 here. 22 says we have a 560 gram squirrel. I'm going to stop right there. Forces are measured in what units? Newtons. And a Newton breaks down to a what? Kilogram meter per second squared. So, hoping little warning lights are going off in your head right now when they gave it to you in grams. Okay. So, 560 gram squirrel with a surface area of 930 square centimeters. Oh. Now the warning light's going on in my head. Because the base unit for area would be square meters, and this is square centimeters. Okay. Falls 5 meters from a 5 meter tree to the ground. Estimate the terminal velocity. Go ahead and use a drag coefficient of what would be the equivalent of a human in a horizontal position. I don't know if that's completely fair, but I don't think they have the squirrel's coefficient in that little chart, so I'm going to go ahead and do what they said. And so if you remember, our little derivation is if you had an object, and I just took kind of a ball and said if it's falling with mg and then has a drag, and if it's going through the air, that drag would be 1/2 times the coefficient times the density times the area times the velocity squared. And so if you wrote out the equations here calling down positive, you would have this mg minus 1/2 coefficient density area velocity squared equals to ma. And this is what we said a little while back, that if you went faster and faster and faster, you'd eventually get to this terminal velocity. And at a terminal velocity, what would be your acceleration? 0. That's what we mean by the same speed. So you can solve this for terminal velocity by setting the acceleration equal to 0. Now, I guess technically we already did that, so you probably could just go back to your notes and look at the equation. But I'm going to kind of work it out from scratch, although kind of quickly here, and say if I move this to the other side, then I'll have just an mg, then I'll bring the 2 to the other side, then I'll divide by the coefficient, then I will divide by the density, I will divide by the area, I will then take the square root. And that's the equation we worked out before the break. What would be the terminal velocity for something moving through a fast, low density medium? Okay. And so now I can find this for the squirrel, but another part of this is to watch your units. So I'm going to use the units and be careful here with it, because I'm going to put a square root. Let me put the numbers here and the units over here. So I'm going to start with the mass. They said the mass of the squirrel, 560 grams. I'm going to put 0.56 and put kilograms for the unit. G is 9.8 in meters per second squared. C is this coefficient they're talking about. So I guess I got to go back to that chart here. Make this a little smaller. Page up, page up, page up, page up. Make it too small, I might miss it. Not there, not that chart. Oh, maybe that was the chart. I think, yeah, typical values of the drag coefficient here. And so, what do they want me to do? A horizontal skydiver? Oh, yeah, that was the one. I guess I should have remembered that one. So there is the 1. The density, and this is what I wanted to help you with. The squirrel's going through the air, sea level. You might have heard me rattle off a number. 1.21 is roughly the density here at sea level. And so I'm going to put 1.21. What are the units? And this is a big reason when you see what are the units? It's a density. Density's what? Yeah, mass per volume. And I need to tell you then that this is kilograms per cubic meter. So that's the density of the air. Oh, and here's another tough one, right? This is why my warning lights were going off. What's the area? The cross-sectional area as a squirrel falls down. Oh, I guess I left it, but I believe it said 930 square centimeters. Yeah. And so I'm going to put right here area 930, and then over here I'm going to put, okay, I will first put centimeters squared, but let me remind you, back to chapter 1, converting units, if you had x times y squared, wouldn't that be x squared and y squared? So centimeters squared should be centa squared and meters squared. And centa means 100th. And so 100 squared is 1/10,000th. So I'm going to replace that with 1/10,000th of a square meter. And so there's my unit conversion. What is the meaning? Remember, use the same rules of algebra for your units and your numbers. And it wasn't cm for centimeters, it was c for centa, m for meter. So I could square my centa and then have the square meter. And that's the easiest way then to convert it. Now, I'll put in the numbers here in just a second, but I'm hoping you kind of see that if I were to just focus on the units here, the kilogram would cancel off. The cubic meter would go to the top and make meter to the fourth, and meter squared down here, and then this would be second squared. Two of these would cancel off, and so you would have meters squared over second squared. So then when you take the square root, you're going to get just meters per second. There's our unit analysis, right? If my units didn't come out in meters per second because they're asking for a speed, I must have done something wrong. And so fortunately, with all these units and all this work, now that we're getting to some really hard stuff, the units match. And so the last step, and we'll get out of here for the next class, is let's put in my numbers. So it's 2 times 0.56 times 9.8 divided by 1, that's a waste of calculator, divided by 1.21 divided by 930, and let me not forget this number hiding over here, divide by 1 times 10 to the negative 4, and then last step, take its square root, and the terminal speed of this squirrel is really pretty low, only 9.9 meters. So as I said earlier, especially for you life science people, things can be a little different for those smaller animals. They don't view quite the same. A squirrel jumping out of a tree, even if it misses the branch and falls 300 feet, 500 feet, 1,000 feet, doesn't go any faster than 9.9 meters per second. Roughly 22 miles an hour. Now that's pretty fast, so it's gonna hurt the squirrel. It's not gonna want to do that on purpose, but it's not gonna kill the squirrel. Of course, it also depends on what it lands on, but that's, no matter how far you fall, you're never gonna go faster than this. And that's totally different than me thinking, I'm gonna jump out of a 300-foot tree. I wouldn't do it. Squirrel would do it. All right, well, got to stop and get going, so I'll say bye to you guys in person and bye to you guys online, then next time. All right.